Most engineers fail the Uber system design interview for one specific reason. They think in terms of databases, not geometry. If you're just using a basic API call to find the nearest driver, you've already lost. At 1 million requests per second, that simple query becomes a death sentence for your latency. I've spent years breaking down distributed systems and analyzing the exact patterns FAANG interviewers use to separate the seniors from the staff engineers. The difference isn't just knowing the components, it's knowing exactly why the standard approach fails at scale. In this video, we're moving past the basics. I'm going to show you how to implement real-time geospatial indexing using Quadtrees and Google's S2 library. We'll build a globally scalable architecture that handles massive concurrency without breaking a sweat. By the end of this, you'll have a blueprint that doesn't just pass the interview, it impresses the interviewer. Most candidates start with the obvious. You think, I'll just store driver coordinates in a database and query for the closest ones. Sounds logical, right? It works for 10 drivers, maybe 100, but you're interviewing for Uber. Now imagine 10 million active drivers globally. Every single one is updating their GPS location every few seconds. Your database is now screaming. You're hitting it with millions of writes per second, while simultaneously trying to run complex geospatial queries for every single ride request. Your latency spikes. Your database locks. Your system crashes. In a real interview, this is where the senior engineer across the table stops nodding. They aren't looking for a working solution. They're looking for a scalable one. If you suggest a basic relational database for real-time driver matching, you've already failed the senior bar. You've shown you can build a prototype, but you can't build a platform. The gap between a mid-level answer and a staff-level answer isn't just knowing the tools. It's understanding exactly why the obvious tools fail at scale. Here is the hard truth. If you tell a FAANG interviewer you'll use a standard SQL query to find the nearest driver, the interview is basically over. Most candidates start with a naive approach. They suggest a driver's table with latitude and longitude columns. Then, they suggest using the Haversine formula to calculate the distance between the rider and every single available driver in the city, on a few hundred drivers. It works. On 1 million drivers across a city like NYC, you've just created a massive bottleneck. Think about the right load. Drivers update their location every 3 to 5 seconds. We're talking millions of updates per second hitting your database. Your disk I/O will melt and your query latency will spike. To pass a senior-level interview, you have to stop searching and start indexing asterisk. This is where geospatial indexing comes in. First, let's talk about geohashing. Imagine the entire world as one giant rectangle. We divide it into 4 quadrants. Then we divide those quadrants into 4 more. We keep doing this until the rectangles are small enough to represent a city block. Each area gets a unique alphanumeric string. For example, Dr. 5 Ru. The magic here is that if 2 drivers share the same prefix, they are geographically close to each other. Now, instead of calculating distances for every driver, your service just asks, who is in GeoHash Dr. 5 Ru? It's a simple key-value lookup. 1 complexity. But geohashes have a flaw, the edge problem. A rider might be at the very edge of one hash, while the closest driver is just across the line in another hash. To solve this, you search the target hash and the 8 surrounding neighbor hashes. If you want to impress the interviewer, suggest a quadtree. A quadtree is a tree data structure where each node has exactly 4 children. As a specific area gets more drivers, the node splits into 4 smaller nodes. This allows the system to dynamically adjust its resolution based on density. In a rural area, the grid is huge. In Manhattan, the grid is tiny. This keeps the number of drivers per leaf node constant and the search time predictable. Now the architecture. You don't put this in a relational database. You use an in-memory store like Redis. Redis has built-in geospatial indexes using sorted sets. It allows you to update locations in real time and query nearby points with sub-millisecond latency. But here is the staff engineer nuance: sharding. You can't fit the entire world's real-time coordinates on one Redis node. You must shard your data by region or geohash prefix to ensure your system scales horizontally as Uber expands to new cities. Now, mastering geospatial indexing is one thing, but passing a full FAANG loop requires a systematic approach. You can't just wing these interviews. If you're struggling to visualize these distributed patterns, I highly recommend Design Gurus or Educative.io. They turn complex architectures into digestible blueprints, so you don't freeze when the interviewer asks about scalability. And for the coding rounds, LeetCode Premium remains the gold standard for pattern recognition. Using these resources is how my students move from confused to offer letter in a matter of weeks. It's about reducing the surface area of what you don't know. Stop guessing your way through your prep. All the links are in the description below. Grab them now and start leveling up.